second, I have to. Okay, so let's take just a closer look at what is meant by spectroscopy, and is the study of interaction of matter with the electromagnetic spectrum. So all these things that have spectroscopy in their names have something to do with how these compounds interact with electromagnetic radiation. What kind of energy in the form of waves? When we direct it at a compound, what do those compounds do? What does it mean? All right, so hopefully you remember a little bit about the electromagnetic spectrum, that it comes in waves. Wavelength is from a consecutive points on the wave, that is the wavelength. The more waves you have that pass by a point per second is known as the frequency. The higher the frequency, the more energetic. Smaller, I shouldn't say smaller, longer wavelengths, you get less waves that pass by a point in a second. Your frequency is low, your energy is low. All right, because remember, these are waves that are traveling through time. You should be familiar that radio waves, microwaves, visible light, ultraviolet light, infrared, X-rays, gamma rays, those are all part of the electromagnetic spectrum. I went the wrong way. Oh, still going the wrong way. All right, so energy of radiation in the electromagnetic spectrum, again, depends on the frequency and the wavelength. The higher the frequency, the shorter the wavelength, the higher the energy. If you remember the equation, E is equal to h times nu, that is Planck's constant times the frequency. That gives me the energy of 1 photon of electromagnetic radiation. Okay. Radio waves, they're going to be used in the nuclear magnetic resonance. And that causes the nuclei of atoms to flip their spin. We have microwaves, we have infrared, which is what we're going to be looking at, and that's stretching and bending of the bonds, and we use this to identify functional groups. We'll look at UV vis, and we'll look at X-rays briefly. So let's focus on infrared spectroscopy for now. It is the stretching and bending of bonds in covalent molecules. Diatomic elements have no infrared spectra, okay, so they don't do anything in this spectrum. Each stretching and bonding vibration occurs with a characteristic frequency, and we can use this characteristic frequency to determine the types of bonds. Okay, if you'll give me, hang on. All right, so here what I wanted to show you was what do we mean by having these bonds rotate. Now, this is an app on an iPad, and because they use a computer model, this is what we're looking at down here is the results from the IR Spec. Now, they're not quite right because they're based on a computer model, so that it's not exactly correct. But what I wanted to show you is what does it mean? And this gives you an idea of what happens. So the electromagnetic radiation is sent into the sample, and the molecule absorbs some of that energy. And if it's at the correct energy, it will make the molecule vibrate. Okay, so it absorbs energy to make things vibrate. And we'll talk a little bit more about it. So you can see that these different peaks kind of correspond to different vibrations within the molecule. And that's kind of all that this unfortunately, all this app is good for, because it is based on a computer model, and they don't have it quite where it's the same as the actual model. But it gives you an idea of what is meant by the vibrations that happen within a IR spec. Okay. So, and this is what a typical spectrometer would look like, an IR spec. Samples kind of go in here, and it reads things, and it prints out a graph that would look like this. All right, and what the graphs typically show you the 100% transmittance up here. This is reading where there is no interaction of the IR, the infrared light that goes through the sample, close enough to 100 that it always absorbs something. But where you see this, meaning that that electromagnetic radiation at this wavelength was absorbed into the sample, indicates that that sample has a functional group that is absorbing that electromagnetic radiation and vibrating. Okay, so we'll see that these troughs, also called peaks, at a certain wavelength indicate that there's a certain functional group that is present in that sample. It is important to note that you can't do a IR using glass or plastic. If you're familiar with the colorimeters, those little cuvettes, you can't do it because those types of materials absorb the electromagnetic radiation in the infrared region. So they're actually done on small plates. These wavelengths, even though they are characteristic of a particular functional group, are going to be slightly different depending on what's connected to the carbon or the adjacent atoms. Okay. So because of adjacent atoms interfering or influencing the vibrations or the wavelengths that are absorbed, no two molecules are going to give exactly the same IR spectrum. Okay, we have what's called a simple stretching, is the 1600 to 3500 inverse centimeters. And then the complex those are simple stretching. Those are what we're going to look at to identify functional groups. And then we have a complex region that's called the fingerprint region that is particular to any one molecule. And that is, it is like a fingerprint. Every molecule has a unique one, and when you're really good at reading IR specs, you can tell the molecule from that region. We are going to focus in on this simple stretching region. So here's what two example ones look like, polyethylene and polystyrene. Here is your simple stretching region. Okay, so you can see that they have similar troughs or peaks around the 3000. We'll look and see what specifically that means in a moment. But you do notice here in that fingerprint region that they are different, and those would be unique to each one. All right, so we're going to talk about or look at examples of characteristic frequencies. And we can see that the carbon to oxygen bond is, we will see a trough or a peak at the wave number 1050 to 1410, and we'll see that this is typically very strong. A carbon to a chlorine is like the 6 to 800 region, which will be difficult to see because that is in that fingerprint region. Same with the CO bond. And then here, the simple stretching, we can see the double bond C, and a C to an oxygen double bond, a carbonyl group. So if we look at this infrared spectrum of propanone, we can see that we have this carbonyl group, and we have this reading here, this C double bond O peak right at that 1700 that we saw on that chart. You are not expected to know or memorize what wave number these different peaks happen. That is table 26 in your data booklet. Okay, so if we look at ethanoic acid, you see this very broad trough in this region, indicating an OH bond in a carboxylic acid. That is very unique. Okay. Then you would look to make sure that it's a carboxylic acid, you would look over here to make sure that I do have that carbonyl group at about that 1700. And then you can look for a CO bond. If this peak is absent, then I don't know exactly what you would have. But if this is absent, then you typically don't have a CO bond. Okay, so maybe you have a aldehyde. I don't know how you'd have this. OH. We'll do some problems. Okay. And then you see in this ethyl ethanoate, you have the typical CH bond, and you see that it is different. It's right around that 3000, but it's not as that broad peak that we see with a carboxylic acid. And then we have, again, that OH bond. Here, and we see an absence of the C double bond over here, so that tells us that it's an alcohol and not a carboxylic. Okay, and then here we can see a CH and a C double bond O, which gives us the aldehyde because I don't have that deep trough that was indicative of a carboxylic.